All right, so in calculus, there are three theorems that are super important. One of them is called the intermediate value theorem. That's what we're going to learn about today. And then at some point in the future, we will learn about the extreme value theorem and the mean value theorem. So intermediate value theorem comes from a principle that should make a lot of sense. Kind of an intuitive sort of thing once I explain it and we write it down. So we say that a function has an intermediate value property if the following is true. If it never takes on two values, without taking on all the values in between. Okay, so again, has the intermediate value property if it never takes on two values without taking on all the values in between. So basically what that means, I want to give you guys two examples to go off of. So think of weather first. The weather will never take on two different temperatures without taking on every temperature in between. Like say you wake up in the morning and it's 62 degrees, and then you check the weather right now and it's 76 degrees, whatever. The way that the intermediate value property works is it can't take on 62 degrees and 76 degrees without at some point taking on every single value in between. Temperature rises, temperature falls, it doesn't just jump. So that means at some point during the day, I don't know when, it was 70.3 degrees. That's one example you can use. Another is your height. Say that when you're born, babies are like, 19 inches long or 20 inches long or something. And let's say now you're 5'5". At some point, you took on every single height in between. There was a point in your life when you were 3 foot, 6.5 inches. Okay? So that's what that property means. And that's a couple of examples that you can think of in regular life. So our theorem, the actual intermediate value theorem, looks something like this. If y naught, so y naught, that little zero is not, and I'm not saying not like N-O-T in a weird voice, it's actually not like N-A-U-G-H-T, whatever that means. So y naught is between f of a and f of b, then y naught equals f of c for some c in a to b. So we're going to write down, this is the formal definition of the theorem. It's going to take some explaining before it makes more sense. So what it basically means is a continuous function will take on every single value between f of a and f of b. So if you're given an interval from an x value of a to an x value of b, your function is guaranteed to hit every single value between f of a and f of b. That's kind of the informal way to say it. This is the official formal mathematical statement. So it says if y naught. So basically, if you pick a y value between the starting y value and the ending y value, you can trace it back to some x value. So if we pick this y value, and we could do it for any y value, we could pick this y value right here. And what this is saying is you can trace it back to some x value that's guaranteed to be between a and b. So let's think of the height example. I said 3 foot 6.5 inches. That would be like a y value, your height. And you'd be able to trace it back to an x value of age. Or again, the temperature of 70.3. You'd be able to trace that temperature of 70.3 back to some point between the morning when you woke up and now. So that's the theorem. Basically what it means is that as long as your function is continuous, it takes on this intermediate value property. And if it takes on the intermediate value property, that means it's going to be continuous because you can't jump to another point. There can't be an asymptote. There can't be a hole. If any of those things were true, you wouldn't be able to carry out this intermediate value property. So that's this statement right here. If you have any sort of discontinuity, even at one point, it might mess up the theorem. It might not. The theorem might still work, but you're not guaranteed that the theorem will hold true unless your function is continuous throughout the whole interval that you're talking about. All right, so this This example right here, we've got a nice little table. The table gives time in seconds and velocity in feet per second. It's very, very, very important that they tell you up front that velocity is a continuous function. Otherwise, like I said, this theorem might not even apply. So here are some velocities, and they'll ask questions like this on the AP test. They love directly questioning your knowledge of the intermediate value theorem. So they'll say something like this. For 0 to 60, so you're looking on this restricted time interval right here, must there be a time t such that v of t equals -5? Okay, so the way that you would do this, and like I said, this will pop up on the AP test too, is you want to see where the -5 would fall. In the velocity column, it's not going to fall in here, it's not going to fall in here, or here, or here, it would fall right here. So you know this y value is -10, and then you know this y value is 0. Think about velocity. Your car can't go from going backwards at 10 feet per second to stopping without at some point going backwards at 5 feet per second. The decelerating has to happen. You can't just instantly stop without at some point having a velocity of -5 feet per second. So what you would do, I mean, you basically would answer yes. Like, yes, you're guaranteed that that's going to happen. So you would say yes, and then basically just make it fit with the statement of the intermediate value theorem. You would say yes because, and then you would set like this first part up here. You would say, you could either say because -5 is in between f of 35 and f of 50. I usually just like to write it like this. It's super easy. You'd say like the velocity at 35 is less than -5, which is less than the velocity at 50. So those are all less than, sorry, they're kind of blended in with the v's and the negative sign. So you start off with this, then you say then v of t equals -5 for some time t in the interval from 35 to 50. So you're almost like restating the intermediate value theorem and just kind of tweaking it to fit the specific context that you're talking about. So you're saying yes, because -5 is somewhere in between this velocity and this velocity, the intermediate value theorem is going to guarantee that the velocity will be -5 at some point. You can't possibly go from -10 to 0 without hitting -5. That's what the intermediate value property tells us. Okay, let's look at another example. Example 2. This one is a little bit different. We don't have a table in front of us. It says, is there any real number that's exactly 1 less than its cube? So what we're going to do is we're going to set up a little equation. So it's any real number, so we could just use like an x. Is it exactly, which means you want to set it equal, 1 less than its cube. So here's its cube, and then there's 1 less than its cube. So you're basically, the way that that question is stated, you're just trying to see if there's a solution to this equation right here. And then it says compute any such value accurate to 3 decimal places. So first, we're going to do kind of an intermediate value property proof, and then we'll go in and use our calculators, and I'll show you how you would get the exact answer. So we're trying to figure out, must this work? And so let's rearrange this a little bit. Let's subtract the x from both sides. So we want to see if this has a solution. That is basically our question, is we want to see if it has a solution. So this is a polynomial. So we know for sure that this function is continuous. That's a guarantee, because when we did that section on continuity, we said that polynomials are continuous no matter what. No holes, jumps, breaks, you're not going to see anything like that. So what we want to do, and I'm just going to give you like some sort of generic, so you know what cubic functions look like. You guys probably call them the chair functions. They look something like this. We know we have a y-intercept at -1, so this is just kind of like a mock of what the equation might look like if it's a cubic. So if this is the case and it looks something like this, we're assuming that there's going to be an intercept right there, because that's what this is solving, is x-intercepts. So basically we want to find a point when you know your graph is going to be below the x-axis, and then you want to find a point where you know your graph is going to be above the x-axis. And if you've got a negative y value, then a positive y value, the intermediate value property says you have to hit every value in between, including 0. So our goal is to find a negative and a positive y value. And that's how we're going to do essentially a proof using the intermediate value theorem. The announcements, they never stop. Okay, at x equals 0, you know, if you plug this in, 0 cubed minus 0 minus 1, of course, is going to give you a y value of -1. So there's your negative value. So you know for sure that right here, your function is below the x-axis. That's an absolute guarantee. So then you just want to check some different ones. So let's see what happens at x equals 1. So if you plug in 1, you've got 1 cubed minus 1, and then it actually goes minus 1 again. So 1 minus 1 gives us a value of -1. So that's not going to help. So this is below the x-axis. This is also below the x-axis. It might peak up above somewhere in between, but we're not really sure. There's no guarantee by the IVT at this point. So let's check at x equals 2. If we plug that in, 2 cubed is 8. Minus 2 is 6, minus 1 is 5. Okay, so that's better. So somewhere in this range, actually, we got our range a little bit more specific. So somewhere in between 1 and 2, we've got a negative y value, then a positive y value. You know you're going to hit a y value of 0 somewhere in between, and that's because your function is continuous. Okay, so let me show you how you do this. You open up a graph page, or if you're on the 83 or 84, your y equals is right here. So type in x cubed minus x minus 1. Let's take a look at the graph. So you can see, actually, see how 0 and 1 have the same y value of -1, and then 2 has a y value of 5. So it is somewhere between 1 and 2 that we're going to cross through that x-axis. So we want to get more specific. Let me show you how to do something on the calculator. If you were on the Inspire, hit the menu key, and then there's an option for Analyze Graphs. You want to hit the number 6, and then you can find either an intersection point. A 0 is probably easiest since we're just looking at one graph. So just select that for 0. And then see down here it says lower bound. So all you want to do, you use this little touchpad, move back and forth, get yourself to the left of where you think the x-intercept is, click down on that middle touchpad, then it'll say upper bound, and then drag over here. Okay, and then click down. So you can see it found that 0. And of course it's not cooperating, it's not displaying 3 digits. So if you just click on this, it should, oh no, of course it's not going to. Come on now. Okay, so let's try something new. So click on that, and then click variable, and we're going to store that as A, I suppose. So now, of course, it's only displaying 2 digits. So again, what I did, I clicked that variable button, and then I just stored it. So now, if you go into any other document and select an A, now it'll tell you. Okay, so that is our intersection point. So if we round to 3, it is 1.325. Okay, so just like we predicted based on the intermediate value theorem, it was in fact somewhere between 1 and 2, and it does make sense that it's a little bit closer to 1 because this is just below the x-axis, this is farther above the x-axis. Okay, a couple more. Example 3 is pretty similar. So we're going to use the IVT, show that this function has a root somewhere on this interval, and so that's basically what you're doing here, and then I'm going to teach you something called the bisection method. So first we want to find the function value at 2.75 and the function value at 3, and so we're going to use our calculator to do this. So you basically just plug in, so 2.75 cubed minus 8 times 2.75, and then minus 1. And then we can do the same thing with 3. 3 cubed minus 8 times 3 minus 1. So we've got those two values, so you can copy them down. So basically, here's the important thing. This came out to be a negative value, and this came out to be a positive value. So that shows that you have a root somewhere on this interval. The function is below the x-axis at this x value, and it's above the x-axis here. So again, because this is a polynomial and it's continuous, you've got to hit a value of 0 somewhere in there. So in the bisection method, this is basically going to help us figure out exactly where that x value is. And we're going to narrow down the interval. So if we know that this is below and this is above, let's cut that in half. Okay, so you're going to cut this interval in half, and halfway in between would be 2.875. Okay, so halfway in between 2.75 and 3 would be 2.875. So we're going to check this one out. So 2.875 squared, and then minus 8 times 2.875, and then minus 1. Okay, so that value is negative. And so we can write, whoops, I should have written, this is less than 0. So this is below the x-axis. This is still below the x-axis. Oops, I'm looking at my calculator screen now. I'm sorry. This, I plugged in something squared. So that should be cubed. Let's try that again. Okay, it's still negative, but barely. That makes more sense. So it's still negative. So the 0 doesn't happen on this interval. It must happen on this interval. So first we thought it was going to be on this interval. And we're right, but we can shrink that interval down. So then we said, all right, we know it's going to be on this interval. So now instead of being a length of 1/4, we got it down to a length of 1/8. And we're asking for a length of 1/16. So to cut this in half, 2.875 plus 3, cut that in half, would be 2.9375. So that's what we're going to check next. Okay, so we're going to see if our function is below or above the x-axis at that point. So 2.9375 cubed minus 8 times that value. Okay, it's positive. It's up above the x-axis. Okay, so my graph was below the x-axis here, above the x-axis here, and then halfway in between it's above. So we know that this one is below and this one is above, so we just narrowed it down. So that is our teeny tiny little interval on which we know that the root is going to fall. All right, last example. This is based off of an AP style problem. So let f be a function. All we have for this function is these two values. So we know if you plug in 2, the y value is 5. We know if we plug in 5, the y value is 2. So they define a new function, f of x minus x. And it says explain why there must be a value between 2 and 5 such that h of r is 0. So what we do is we kind of go back to the idea here. They gave you an interval, and what's really important in the statement of the IVT is what's happening at the function values there. So since we're talking about h, we want to figure out what h of 2 is and what h of 5 is. Okay, so we use this definition right here. So this is f of 2 minus 2, and f of 2 is 5. It's defined right here. Okay, so the new definition of our function says that h of 2 is equal to 3, so we've got that. And then define this. So f of 5 is defined as 2. This is negative 3. All right, so it says explain why there must be a value r between or on this interval such that h of r equals 0. So you know that h of 2 is 3, and you know that h of 5 is negative 3. And so based on the IVT, remember we can go back here and kind of state that. So if y is between f of a and f of b, so we can say since h of r equals 0 is between h of 2 and h of 5. Okay, and then, whoops, sorry, that's off the screen. I'm going to go back. Then y naught equals f of c for some. So then we can say then, actually we don't really need this. Let's say then h of r equals 0 for some r in, and then restate that x interval. So you're basically, like I said in the previous problem, you're just taking the intermediate value theorem, plugging in the actual numbers for the problem, and kind of restating it. All right, so that's it.